Here we have a project for regression analysis. We'll consider linear, piecewise linear, and nonlinear models. Regression analysis is a statistical process for estimating the relationships between independent variables and dependent variables. It is a way to find trends in data. There are variations, linear, multiple linear, and nonlinear. The most common models are simple linear and multiple linear. Nonlinear regression analysis is also commonly used when the dataset shows a nonlinear relationship. The selection of an appropriate regression model is often a difficult task. In this project, we'll try to find best regression models for given datasets. Here is a strategy for the determination of the best model. Once the dataset is given, then we may try to plot the dataset for a visual inspection. And look at this dataset. Maybe you think that the best model is a quadratic polynomial. One or more good models can be selected. Then the best model is determined through analysis. For this one, it looks like a quadratic polynomial. Here we have a review for polynomial fitting for the data set. And as in the figure, consider a regression model of the form. This is a quadratic polynomial. And for each point, we can get predicted y values and observe the y value. For example, for x1, y1, the first point, we have this predicted y value, and y1 is the observed y value from the data set. For each point, we have an equation, and this set of equations can be written as in this metric form. Of course, x must be the collection of quotients. For A0, all ones are the quotients. For A1, the collection of x coordinates, and for A2, the collection of x coordinates squared. This is unknown vector, and y is the observation vector. We can solve the system by using the method of normal equations. Okay, this is a review for polynomial fitting. The polynomial fitting is well implemented in most programming languages. In MATLAB, you may try to use polyfit. X is the collection of x values, and y is the collection of y values. And degree means the polynomial degree. In Python, also you can use the function having the same name, polyfit. The same way you can use it. The polyfit is under the NumPy library. So you have to import and call it this way. And rather than implementing this the method of normal equations, we'll try to use built-in function in this project. See this program, and the data set is read in the beginning, and first column is x, and second column is observed values, y values, and biasing x and y with degree 2. So its output will be quadratic polynomial. The P will include only the coefficients A2, A0, A2, A1, A0. The first one is for the x squared term, so it's A2. The second one is A1, and last one is the for the constant term. By using the coefficient, we can evaluate the values at each point in this array. So that y hat is the predicted y values. So here we can measure the least square error, and y, that is data value, and that is predicted value, and difference is measured. We measure the L2 norm and squared and divided by length of y, and that is a form of variance. But you can measure least square error in this way. It is we have a printout and least square error and the P that you see here now. I copied the output of that line, and error is 0.13, and P has 3 components. There's A2, A1, A0. Okay, this below portion is for figuring. Okay, let's see here figure. And is the quadratic model is superposed over the data points, and it is representing the data quite nicely. Okay, we'll go to nonlinear regression. See this data set, and it looks like exponential function. So data set name is seemingly exponential data. So we consider a model of this form. Then the corresponding nonlinear least squares have this objective. We have to minimize these least squares and try to find the C and D, which minimizes this quantity. This problem can be solved by applying a nonlinear iterative solver such as the Newton's method with a good initialization. Here, your initial value must be good. If not, then there is no guarantee for convergence. So it is a little bit complicated. We can solve the problem much more easily through linearization. Okay, let's see a way of linearization. We start with this model, and the goal is to find best C and D such that this model fits the data set best. First, we apply transformation. For example, the logarithmic function can be applied to the equation. Then logarithm y equals logarithm of this right side. By using the logarithm laws, we can have that. And logarithm, exponential, they are inverse each other. So we can get here, this term becomes dx and logarithm c. Now we apply change of variables. We don't have to use another variable, but anyway, we try to introduce capital X for small x. Now for logarithm y, we use capital Y. And for here we have a for logarithm c. Then this equation can be written in this form. Y, capital Y equals now d times capital X plus a. Now this is a linear model, and we can get here DNA by using X and capital Y, and we can get, and along with degree 1, we can get DNA quite easily by calling this function. After getting it, here A is logarithm C, so that C can be recovered with this formula. C is e to the A. Okay. Here is a program. After reading the data set, and here this is a mathematical formula, and once we try to fit the data in this form, then now after applying the logarithmic function, we recheck this one. Now from data set, first column is X, second column is Y, and now change of variable is here. Okay, we have a change of variable here. Of course, for this one, you have to transform the data along with that change of variable. So Y, from Y, we try to get logarithm of Y. I'm sorry. And now X is the same. Now Y, this is logarithm Y, and polynomial degree 1. And we can get P. P1 is related with D, and the second component of P will be here logarithm C. And D can be assigned from the first component, and C can be obtained from the second component of P and with exponential function. So we get that one. Now here, this portion is predicted Y values. This is observed Y values, and again, we can measure the least case error in the form of a variance. And after printing out and C and D and least squares error, and we have that C is this quantity and D is this one, and that is the error. And this portion is for figuring, but it is the portion. Okay, let's see the figure, the data set and the nonlinear model, and that is here Y equal this times an exponential 0.669 times X is fitting well. If you want to test the program, you may download by clicking these two. The data set has 200 points generated by this function with random positioning and random noise. After perturbation, you can see here quite similar. Because of random noise, it is changed there. Okay. Now we'll go to here issue of finding the best regression model, and see this figure from a sine curve, and we select a value and add some noise. So these squares are data points, and for these data points, let's try to find a good polynomial model. So the Pn is nth degree polynomial, and let's try to choose the best n among polynomial models. Try to find the best polynomial model for this data set. Okay. Okay, let's see the program. Here, A0, B is 1, it's A and B, and m is 10, I chose 10 points over there, and f is sine 2 pi t, and here, okay, this portion is how I generated the data. And here, along with once the file exists, and here renew data is 0, that means that try to use saved data. And if not, then here we try to generate and first make such points, and then noise is made, random noise, and so that this noise has mean 0 and added to here y0 and finalize that data by collecting x and y and save into the data file. So once you choose here renew 1, then it is making again. If it's 0 and if there is a file in the directory, then it will use it. Okay, this is not a main part of the program. This is how I generated the data set. Okay, now this is the main part. And once you read the data, then the first column is now x coordinates, and second column is y coordinates. And by using that, you can get polynomial feeding with n. N is now moving from 0 to n minus 1. So in the beginning, constant polynomial, and next one will be linear polynomial, and next one is now quadratic, and followed by cubic polynomial, and so on. And after getting it, here that one, after doing that, this one is the least squares. Error is saved. Okay. Now, this portion is for producing a figure, and here also below there are some portion, but I erased that. Okay, so major part is just polynomial feeding and polynomial values, and try to get the corresponding least squares error. Okay, that's the main part. Once you are using Python, then also for that polynomial value, you can find the same name in Python. And for this portion, reading metric, you have to use here in Python road text. And for writing, you have to use save text on the NumPy package. Okay. Okay, here we have figures. Now this is constant regression, linear regression, quadratic polynomial, and degree 3, 4, and 5 is almost the same as here, so that we jump to 6, and degree 7, and 8, 9. Okay, 8, 9, this is a start oscillatory. So it looks like these are almost the same. In this case, you may have to choose degree 3. Here is a strategy. Given several models with similar explanatory ability, the simplest is most likely to be the best choice. Because it's simple, and so that computationally cheaper. And once you try to get a very complicated model, then in polynomial, easily oscillatory, in machine learning sense, we say in this case is overfitting. So when you try to choose good model, then start simple and only make the model more complicated as needed. Okay. Here, the least squared measured from the program for each n is given here. So that is called the mean square error. And once it's 0, then large, and here, and 1 and 2 is going down, and 3 is all of a sudden very small, and 4, 5, 6 gradually go down, but almost the same. And mathematically, when you are choosing n equal 9, then the error must be 0, because here, now this is 9th degree polynomial for 10 points. The polynomial is passing all the points, so that it must be 0. The error must be 0. Okay. However, from also this figure, we can choose degree 3, that is the third order polynomial. That's the best choice. We summarize here, so far we have done, and we reviewed the method of normal equations and consider example polynomial fitting and nonlinear regression and its linearization. And also we considered a strategy for the determination of the best model. Okay, here, this is the project objective. Find the best model for each of the data sets. We have 2 data sets. First, you have to download these data sets by clicking or writing these 2. And now the first step is you have to find the best models for data 1. You may think this is quadratic or exponential. You have to check, you have to find a model for both of them. And then here, try to check the least squares error. And you have to choose the one which has a smaller least squares error. And for the second, the data set, if you try to find polynomial models, then which order of a polynomial is fitting the best? You have to answer that one. And your answer must be supported pictorially, as in figure P.4, like this one over there, that one. Try to make superpose your curve and try to see if the model is really well fitting the data set. And if you try to add some the degree, then from certain moment the model will be oscillatory. Once it is oscillatory, then it's not so good. So you have to choose some degree so that it is well fitting, but there's no oscillations. Okay. Now for every the model, you have to verify, and along with measuring the least squares error, and also for the second data set, you have to display the least squares error, and also in figures. And here you have extra credit problem. Find a piecewise regression model for the second data. If you try to find a piecewise regression model, then is it better than polynomial models? And by checking the least squares errors, and you can verify, you must verify your answer for this one. Okay, look at this one. Looks like here partly linear, or this is linear, but that looks like a little bit bent, and so that you may consider linear. In order to do that, you have to separate the data set. Look at here around 3.3 or 3.4, around there. This is a portion, there is another portion. And you have to separate the data set into two portions, and for each portion, try to find linear. If you consider this one is quadratic, then okay. And under your choice, you can make here regression and here separately. And then along with that, now you can find least squares error from here, the least squares error from here, and addition is the total least squares error. If this total least square error is smaller than any of those for polynomial regression, then you can say the piecewise linear model is better than polynomial models. Okay, so try to verify. You may use parts of the code shown in this project, report your code, numerical outputs, and figures with a summary. Unverified codes will not give you any credit. So you have to verify for every claim of yours. The summary will be worth 20% the full credit, include all into a single file in a PDF format or Microsoft Doc or docx format. Okay, that's the end of project. Thank you.